The deepest we've ever seen into the sun, SDO 4K. Did you know that no other spacecraft has gone as far as the Solar Dynamic Observatory? This spacecraft gives high-resolution images of the closest star, the Sun, in our own galaxy. The Solar Dynamics Observatory, SDO, is a NASA mission which is part of the Living with a Star (LWS) program that has been observing the Sun since 2010, and after it was launched on 11th of February that same year. Click the like and subscribe buttons as everything about this spacecraft SDO is explained for better understanding. The Living with a Star (LWS) program is targeted at developing the scientific understanding that'll help to address those aspects of the connected Sun-Earth system that directly affect life on Earth and its society. With the Solar Dynamics Observatory (SDO) being an LWS program, it'll help to understand the influence of the Sun not just on the Earth, but also near-Earth space by studying the solar atmosphere on small scales of space and time and in many wavelengths simultaneously. The target of this program is to demonstrate how the Sun's magnetic field is generated and structured, how this stored magnetic energy is converted and released into the heliosphere and geospace in the form of solar wind, energetic particles, and variations in the solar irradiance. The SDO spacecraft is a NASA's mission that was developed at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and launched on the 11th of February 2010 from Cape Canaveral Air Force Station, CCAFS. SDO is considered by some to be a follow-on mission to the Solar and Heliospheric Observatory, SOHO. SDO is a stabilized spacecraft that is composed of 3 axes, 2 solar arrays, and 2 high-gain antennas, in an inclined geosynchronous orbit around Earth. It has 3 instruments that together observe the Sun almost continuously and take terabytes of data daily. These instruments include the Extreme Ultraviolet Variability Experiment, EVE, the Helioseismic and Magnetic Imager, HMI, and the Atmospheric Imaging Assembly, AIA. The Helioseismic and Magnetic Imager, HMI, was built in partnership with Stanford University in Stanford, California, and led from there. It studies changes in solar activities, such as the changes in the amount of radiation emitted by the Sun and changes in the solar wind. It also characterizes the Sun's interior and the various components of magnetic activity. HMI studies the magnetic field at the solar surface and takes high-resolution, 1 arcsecond measurements of both the longitudinal line of sight and vector magnetic field by viewing the full Sun's disk. It does that with emphasis on various concentrations of metals in the Sun, with a range centered on the solar spectrum's 617.3 nm Fraunhofer line. The light is passed through 5 filter instruments, including a layout filter and 2 Michelson interferometers to rapidly and frequently create Doppler images and magnetograms, which are maps of solar surface velocity and maps of photospheric magnetic field respectively. The HMI is the successor of the Michelson Doppler Imager, MDI, on the Solar Heliospheric Observatory, with improved full-disk focus and advanced magnetometers. The MDI instrument could only focus within the line of sight with limited magnetic data. The data produced by HMI are used to determine the interior sources and mechanisms of solar variability, and how the physical processes include the Sun and the surface magnetic field and activity are related. For studies of variability in the extended solar atmosphere, HMI also produces data that can be used to estimate the coronal magnetic field. The observations made with HMI enable the establishment of the relationships between internal dynamics and magnetic activity, and as such understands solar variability and its effects. HMI comprises a refracting telescope, a polarization selector, an image stabilization system, a narrowband tunable filter, and 2 4096-pixel CCD cameras with mechanical shutters and control electronics. These instruments work together to produce nearly continuous data. The Extreme Ultraviolet Variability Experiment, EVE, was built in partnership with the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics, LASP, and was delivered to NASA Goddard Space Flight Center on the 7th of September 2007. It's designed to measure the Sun's extreme ultraviolet, EUV irradiance. It has some improved features over preceding measurements made by TIMID-C, SOHO, and Source XPS, which includes improved spectral resolution, temporal cadence, accuracy and precision. Further scientific understanding of the relationship between solar EUV variations and magnetic variation changes in the Sun requires that EVE incorporates physics-based models. The Earth's upper atmosphere is primarily heated by energetic extreme ultraviolet photons from the sun, and this heated atmosphere forms the ionosphere, ionized plasma. The EUV radiation from the sun undergoes both moment-to-moment and over the sun's 11-year solar cycle constant changes that their understanding is of great importance. This is because they have a significant impact on atmospheric heating, satellite, drag, and communication system degradation, including disruption of the global positioning system. EVE provides up to 70% improved spectral resolution measurements in the wavelengths below 30 nm, and a 30% improvement in time cadence by taking measurements every 10 seconds over a 100% duty cycle. In order to measure all EUV wavelengths simultaneously, the EVE is designed to include grating spectrographs with array detectors. The Extreme Ultraviolet Variability Experiment instrument has a size of 100 centimeters by 61 by 36 centimeters and a total weight of 61 kilograms. It has an average power of 60 watts, but can peak up to 137 watts. The Atmospheric Imaging Assembly, AIA, built in partnership with the Lockheed Martin Solar and Astrophysics Laboratory, LMSAL, as well as led from there. It uses 4 telescopes that use normal incidence, multi-layered coating optics to provide narrowband imaging of 7 extreme ultraviolet UV channels. AIA provides continuous high-resolution full-disk observations of the solar chromosphere and corona. AIA spans a temperature range of approximately 20,000 Kelvin to 20 million Kelvin when in excess. The 12-second cadence of the image stream with 4096 by 4096 pixel images at 0.6 arcsec per pixel provides unprecedented views of various phenomena that occur within the evolving solar outer atmosphere. The Atmospheric Imaging Assembly captures the sun every 12 seconds in 10 different wavelengths. The AIA science investigation is led and operated by LMSAL, which jointly with Stanford University runs the Joint Science Operations Center, from which all of the data are communicated to the scientific community around the world, as well as to the general public. LMSAL designed the overall instrumentation and led its development and integration. AIA has operated successfully with unprecedented EUV image quality since beginning its operational phase on the 1st of May 2010. For Sun-Earth communication, SDO has 2 onboard high-gain antennas through which science data K-band are sent down and 2 onboard omnidirectional antennas that send down telemetry S-band. The ground station consists of 2 dedicated, redundant 18-meter radio antennas located in White Sands Missile Range, New Mexico, and specifically constructed for SDO. The spacecraft is operated remotely by mission from the Mission Operations Center at NASA Goddard Space Flight Center. The combined data rate is about 130 mbits per second. Every data collected by the craft is made available as soon as possible after it's received. SDO after launch was placed into an orbit with an initial perigee of about 2,500 kilometers, 1,600 miles around the Earth. It then underwent a series of orbit-raising maneuver that eventually adjusted its orbit until the spacecraft reached its pan-circular geosynchronous orbit at an altitude of 35,789 kilometers, 22,238 miles, at 102 degrees west longitude, inclined at 28.5 degrees. This orbit was chosen to allow for uninterrupted communications to and from the fixed ground station, as well as to minimize solar eclipses to about an hour a day for only a few weeks a year. The alignment of ice crystals that were forming a sundog visible to onlookers were destroyed in the sky by the visible shockwaves created by SDO's Atlas V rocket when it penetrated a cirrus cloud moments after launch. SDO is the first mission to be launched for NASA's Living with a Star (LWS) program that keeps a constant eye on the sun, track everything from sunspots to solar flares to other types of space weather to better understand the sun's influence on Earth and near-Earth space by studying the solar atmosphere on small scales of space and time and in many wavelengths simultaneously. Just according to plan, SDO has kept a constant eye on the sun over past decades, studying how the sun creates solar activity and drives space weather. Since its launch, it has collected millions of scientific images of the sun, thereby giving new insights to scientists on how it works. February 2015 marks 5 years of SDO in space, and to honor the 5th anniversary, NASA released a video of highlights from the previous years of sun watching, from which giant clouds of solar material hurled out into space, the dance of giant loops hovering in the corona, and huge sunspots growing and shrinking on the sun's surface. During the course of the video, the sun subtly increases and decreases in apparent size. This is because the distance between the SDO spacecraft and the sun varies over time. The essence of capturing images of the sun in 10 different wavelengths is that each helps highlight a different temperature of solar material. Different temperatures show specific structures on the sun. For instance, solar flares are giant explosions of light, and X-rays, while coronal loops of streams of solar material traveling up and down looping magnetic field lines. These occur at different temperatures. A remarkable video of a 4K view of solar flare from the sun was observed the following year. The question became, is the flare harmful to humans? The answer to this question is very simple, but before then, if you're enjoying this video, don't hesitate to click the like and subscribe buttons. On April 17, 2016, a 4K view of the solar flare was captured by SDO. From the movie of the year, a mid-level solar flare seen as a bright flash of light was released from an active region on the sun's right side. Although solar flare is a powerful burst of radiation, harmful radiation from it cannot pass through Earth's atmosphere to harm humans on the ground physically. Rather, when intense enough, they can cause disturbances in the layer where GPS and communication signals travel. The flare seen in April 2016 was of moderate strength and only caused brief radio blackout as reported by NOAA's Space Weather Prediction Center. This solar flare video is captured in several wavelengths of EUV light that is invisible to the eyes, but for easy viewing is color-coded in SDO. As much as the sun is always changing, one great relief is that NASA's Solar Dynamics Observatory is always watching. SDO still maintains its target of producing tantalizing images of the sun and gives information right from the interior of the sun. Moreover, studying our closest star is one way of learning about other stars in the galaxy. During the 10-year anniversary of SDO living with the sun, in February 2020, it was made clear that SDO is expected to remain operational until 2030. If you enjoyed and learned something about the SDO, please subscribe to this YouTube channel to view a lot more on SDO and other spacecraft.